Today we'll be discussing about the interfacial properties of suspended particles. How these properties play a major role in sustaining and in improving the stability of a pharmaceutical suspension. In today's lecture, we will be discussing in detail about the properties of suspended particles that play a role in improving the stability of a pharmaceutical suspension, which include surface free energy and electrical properties. What is a suspension? Suspensions, they come under the category of dispersed systems. Dispersed systems are the dosage forms having both phases, dispersed phase and dispersion medium. Now, suspension is a biphasic liquid dosage form having both dispersed phase and dispersed medium. Now, this dispersed phase includes a finely divided particles of the drug, and dispersion medium is the external phase. In a suspension, dispersed phase is finely divided and uniformly distributed in the dispersion medium. Now, each finely divided particle size would range from 0.5 to 5 microns. These suspensions are normally used orally, can be categorized as parenteral suspensions, and also these suspensions can be applied externally over the skin. Now, why these suspensions are considered as a stable dosage forms when compared to solutions? Why? Because most of the drug particles or the drug substances, when they are solubilized in water or other solvents to make a solution or to produce a solution, in this solubilized state, the drug particles might undergo hydrolytic reactions and thus producing and thus getting subjected to degradation. So to avoid such hydrolytic reactions, most of the drug particles, they sustain or they exist in a stable state when they are formulated as suspensions. So in suspension, they exist as finely divided solid particles, insoluble solid particles distributed uniformly in a dispersion medium. So there is no chance of getting solubilized nor getting degraded. So the drug particles which show hydrolytic reactions, which undergo hydrolytic degradation, such drugs substances are chosen to be formulated as suspensions. Now, let us see what are the properties that play a role in the stability of a suspension. Let us see the interfacial properties of suspended particles. The interfacial property of a suspended particle includes surface free energy and electrical properties. As a suspension consists of finely divided particles, let us consider this is a beaker having suspended particles in a dispersion medium. Let us consider this as a suspension. So this is a dispersion medium and these are the suspended particles, dispersed particles. Now, as a suspension is a finely is a biphasic liquid dosage form having finely divided solid particles in evenly distributed in dispersion medium. As these are finely divided, now let us consider each particle. As each particle is finely divided, there is a chance of, now let us consider this as a particle. So each particle will have a surface charge as it is finely divided. So each particle will be having some surface charges existing. Either it could be a positively charged or a negatively charged based upon our drug nature. So each particle will be carrying a surface charge and also surface free energy. Now let us consider, why does a solid particle have a surface free energy? Let us see in detail. As a suspension consists of finely divided particle, when we size reduce a particle, the particle size gets reduced, and at the same time particle surface area gets increased. Let us consider a surface free energy. Now when a particle is size reduced, particle surface area increases and also particle surface energy also increases. Right? Now when a particle surface free energy increases, all these particles will try to have instability. They'll move away from each other because of a higher surface free energy. They'll not come closer. They'll not form floccules. They remain as thermodynamically unstable. So we being a pharmacist, we should make sure that the surface free energy of all these particles should be reduced, and all these particles should come together and form floccules. They should come closer and form floccules so that the surface area of each particle will be reduced and surface free energy also gets reduced, and all the particles will come closer and they form a loose fluffy mass like loose network, which are known as floccules. So we being a pharmacist, we should make sure that the surface free energy should be reduced, and also the stability will be thus increased by promoting flocculation. From the formula of a surface tension, which shows the work done is equals to surface tension into the change in the surface area. By making use of the same formula, we can get the formula for surface free energy. Surface free energy delta G is equals to interfacial tension that exists between the liquid and the solid. So as we are considering a beaker with suspended particles, so each suspended particle has an interface having a solid surface and surrounding liquid surface. So the interfacial tension that exists at the solid surface and the liquid interface into the total surface area. Here, each particle surface area would be considered. Because of size reduction into finely divided solids, some work will be done, and at the same time there will be change in the surface area as surface area gets increased, and thus the surface free energy also increases. So that relationship is given by this equation: delta G is equals to interfacial tension into the change in the surface area. So we being a pharmacist, we should make sure that we should improve the stability by reducing the surface free energy. So when a surface free energy reaches zero, then the system becomes thermodynamically stable. So this reduction of surface free energy can be done by surface free energy reduction can be done by two ways. The first one would be either by flocculation or either by aggregation of particles. Now here we need to know about the difference between the flocculation and aggregation. Flocculation is the formation of loosely packed network of particles, whereas aggregation is the tightly packed particles. Now for a suspension to be said as a stable one, the particles should be flocculated. It is a desirable property of a stable suspension, whereas aggregation represents a hard cake formation. So the acceptable way to reduce surface free energy is by flocculation is considered. So how can we improve flocculation? We being a pharmacist, how can we improve flocculation? By addition of flocculating agents. And also the interfacial tension can be reduced by the addition of wetting agents. So addition of flocculating agents or the wetting agents will improve or will help the suspended particles to undergo flocculation or the aggregation. So it is always important to add wetting agent or the flocculating agent to improve flocculation or to promote flocculation among the particles. The next one is the next property by which we can study and improve the stability of a suspension is electrical property. Electrical property. So, electrical properties play a really major role in studying the stability. So, as the suspended particles carry surface charges, these surface charges play a role in either forming attractive forces or forming repulsive forces between the particles. So normally the repulsive forces, they result from the interaction between each particle, and the attractive forces, they result from the van der Waals forces of attraction between the particles. Now let's see in detail. This is an important consideration to be considered when we are establishing a stability of a suspension. Now let us see. Now this is a stable suspension where the suspended particles are uniformly distributed, and when this suspension is kept as such for undisturbed for some time, all these particles will tend to come closer. Now, they'll tend to come closer. And when it is left undisturbed, all the particles, they'll not form floccules, but rather they'll just come closer and they'll try to get sedimented at the bottom of the container like this. And during this procedure of sedimentation, all the particles, when they come closer together, they'll form some attractive forces. The attractive forces will get developed between these particles and they are tightly packed, and thus they get sedimented, and this results in hard cake formation. Even when this suspension is shaken, this hard cake will not be redispersed again. So now let's see what actually happens between these particles, how the electrical charges are developed on these particles, and how these electrical charges play a role in formation of hard cake or in the formation of floccules. Always remember, we being a pharmacist, we should make sure that the particles should form floccules, should not form hard cake. So we should make sure that the electrical charges are evenly distributed throughout the system or throughout the dosage form in such a way that floccules are formed, means loosely packed aggregates are to be formed, are not the tightly packed aggregates to be formed. Now let's see in detail. So when particles are coming closer, imagine suspended particles in dispersion medium let's consider this as your container. Okay, I'm not so good at drawing. Okay, let's consider these as the particles, suspended particles. So as we know, all these particles will exhibit surface free energy and surface free charges. Now we need to consider, as we are discussing about the interfacial properties, we need to consider this part, the interface of the solid and the liquid. So let's consider this each particle and then we'll discuss. So let's consider each particle. Now let this be your particle and this is your interface, right? Now for example, if the considered drug particle is positively charged, okay, so let me consider this one, a positively charged drug particle in a beaker having dispersion medium. Okay, now what can we expect? For example, if this medium has both positive charges and negative charges, okay, positive charges and negative charges, what would be the fate of this positively charged drug particle? It would attract negatively charged particles, right? Negatively charged particles. So what would be the fate of these negatively charged particles when they got attached to this positively charged drug particle. Now, this negatively charged will have a tendency to bind with or to attract positively charged particles present in the medium, and again the positively charged particle of the drug, right? So means what here? Because of these charges, the drug particles are loosely held together with the help of these charges, right? It could be either negative charges or the positive charges based upon the charge of your drug particle. So that is how the electrical properties of a suspended particle play a major role in the formation of aggregates, a loosely packed aggregates. Now let's see in detail. So what kind of charges actually exist between these two particles? So actually there will be different type of potentials that exist. For example, here there will be a different potential that exists. Say for example, here from positively charged drug particle and negatively charged, here there would be one potential that exists, and here there would be another potential that exists. And in this negatively charged ion, if this gets attached to a positively charged, and this again negative charge, and this again positive charge, so as the distance from the drug particle increases, the potential between or across the drug particle and the surrounding also changes. The potential gets decreased. The potential that actually exists on the surface of the particle will be more when compared to the potential that is distributed in the dispersion medium. Now, that concept we are going to see in detail. Let's see. In detail about the potential that exists. And let us even discuss about this graph in detail. In the next slide. In the next slide, we will be discussing about the surface charges and the surface energy carried by each suspended particle. Now, let us consider this one as your beaker and this having a suspended particles. When these suspended particles are this suspension is left as such undisturbed, all the particles will tend to come closer and they'll form and they'll get sedimented slowly together. This is what happens in a deflocculated suspension. But in case if we are considering uh, a flocculated one, okay, let's consider a flocculated one. In a flocculated one, we'll be able to see the formation of floccules, like a loosely packed, okay, all the loosely packed together, a loosely formed network. So even if it gets sedimented, it will not form a hard cake. Rather, all the loosely arranged particles, they form as network there will be some networking seen between the particles, and this is known as a flocule. And when all the floccules they undergo sedimentation, of course the sedimentation volume would be higher and no hard cake is formed. So during this process of flocculation or hard cake formation, all the particles when they are coming together, they need to overcome some energy potential that is present across the particle. Now let's consider this graph. This graph is an energy curve. Now consider this as a particle. Here you're having one particle and here you're having another particle. Now this is a container having suspensions, suspended particles. Now when a particle is coming closer to another particle, because of the surface energy on the surface charges, when this particle is coming closer, this particle has to overcome some energy or the surface charges. When we are considering two particles, now let's consider this one. So okay, now these two particles have both repulsive forces and attractive forces based upon the charges they possess. Now let's consider this one. When there are more repulsive forces between these two particles, when they are supposed to come closer, they need to overcome a high potential because both are having a repulsive forces. They need to overcome the higher potential barrier. So because of this higher potential barrier, these cannot come closer, these particles cannot come closer, rather they remain as a deflocculated one. So when a particle having both the repulsive forces, when they are supposed to come together, they cannot come together because of the highest potential barrier. So we need to make sure that the potential barrier is reduced and we need to improve the attraction forces between the particles so that these particles will form aggregates. So when these particles form floccules or loosely formed network, then this suspension would turn to be a stable one because of the flocculation. So if the potential barrier is higher, each particle will remain as individual entities and they'll not form floccules. They will get settled down as individual particles like this. They get settled, and when they are getting settled, because of the forces between the particles called attractive van der Waals forces, so when all the particles come closer and form the attractive forces, they form a hard cake, like this. A hard complete aggregation of the particles takes place, and this results in the hard cake formation. So in a deflocculated suspension, During the hard cake formation, the repulsive forces and both the attractive forces play a major role. The highest the higher potential barrier between the particles will make the particles to remain as individual entities, and they get settled down. And when they get settled down, when they all the particles will are coming closer, and because of this the formation of attractive forces, van der Waals forces between the particles, they form as a hard cake. So even then, if you shake vigorously the container, the hard cake will not be redispersed because of the attractive forces. So, and thus, deflocculated suspension is said to be unstable because of these charges or the forces or the potential energies that exist. So, we being a pharmacist, we should make sure that we should reduce the potential barrier. We should reduce the potentials, electric potentials between the particles, right? And now, this is how it is explained. This aggregation of the particles into a hard cake is explained by this graph, where when the two particles, this is with respect to the distance. This, for example, say if here you're having one particle and here we are having another particle, how the potential energy varies with the distance between the particles. So when a particle comes closer, it actually enters the primary potential where the energy barrier is overcome by the particle, and thus all the particles will come closer and they form a hard cake. And that is how the surface charges play a major role. Now, we being a pharmacist, we need to know how to improve the stability, how to make a suspension as a flocculated suspension, not a deflocculated one. So, we need to overcome this energy barrier. So, to overcome this energy barrier, we need to impart high energy, or we need to impart stress forces, which is known as, in a normal language, which is known as a vigorous agitation. So, when you shake the suspension, suppose this is a deflocculated one, this is a flocculated one. So when a suspension is said to be a stable one if and only if after redispersion, after shaking vigorously, it should be able to form loosely packed particles. If it is not able to form a loosely arranged particles, or if it is not able to redisperse properly all the particles, it remains as a hard cake or a closely packed containers, closely packed particles in a container. So to it is the duty of a pharmacist to overcome this energy barrier. So therefore the particles should always be maintained at a distance of 1000 to 2000 angstroms in the secondary minimum. It is known as a potential. From the curve we'll be able to see from this curve, we should always make sure that the distance between the particles should be at least a minimum of 1000 to 2000 angstroms. So the distance of 2000. So when can we actually maintain a distance of 1000 and 2000 angstroms? If and only if we are able to overcome this potential barrier, and if we are able to balance the repulsive and attractive forces, and if we are able to uh, promote flocculation, then only we can maintain a distance of 1000 to 2000 angstroms. So this Why only 1000 to 2000 angstroms? Because that is a distance where it can easily form a loosely packed floccules, a network of floccules. So now let us discuss how can we improve the stability by considering the surface charges. It is really important. For example, it is actually really important to consider the surface charges or surface potential. Suppose this is a beaker having a particle which is a positively charged. Okay. Now this is a suspension having positively charged finely divided drop particle suspended in a dispersion medium. Okay, now we are discussing about a concept called electrical double layer, which is a phenomena that exists on the surface of the suspended particles. Okay, now for example, if this the drug particle is positively charged, this drug or the drug particle having positive charges will actually influence the distribution of ions in the solution surrounding them because of the charge that is carried by this particle. Right? Now let's focus on this graph and on this illustration. Now from this graph you are able to see the particle, right? You're able to see the particle here, the particle having positively charged, right? Now here the same, we have taken the same example here, the positively charged. Now we are going to discuss about the distribution of charges in the suspension, and at the same time in parallel we are able to discuss about this graph. Okay, now because of this positively charged drug particle, this positively charged drug particle will attract the negatively charged particles, right? The negatively charged one from the solution, right? So when we are able to see in this graph, so on this positively charged particle, it is able to attract negatively charged, right? Now at this immediate surface there would be one potential. All the negative ions that are attracted and that are held close to this solid surface, this layer, the immediate layer on the solid surface having negatively charged, is known as Stern layer. Now we have considered positively charged drug particle as an example. Even we can, the same happens vice versa with a negatively charged drug particle. If we take negatively charged drug particle, here it would attract positively charged ions. So this immediate layer is known as Stern layer, that is held very much closer and tighter. This layer is very tight layer. And at the same time the positively charges will be repelled from the surface. So a layer of the dispersion medium will be absorbed onto the solid surface. Now because of this migration of negative ions towards the solid surface will actually cause some movement will actually cause the migration of positive ions away, positive ions of the dispersion medium away, and the negative ions will come closer to all the particles, the drug particles. Okay. So this causes, because of the thermal motion within the medium, also influences the distribution of all these ions. Now, as a result of all these movements, uh, when there is, when we move forward, here it would be a strong tight bound layer of negative ions. Now, as we move further, as we move away, distant from one particle, we are considering only one particle, drug particle. Now here the distribution of ions gets diffused. Here it will be more negatively charged ions, and the positively charged ions, negatively charged ions will be seen as we move distant, as we move away from the particle that we are discussing. Means what? Here there will be some diffusion of ions, not tightly bound. Here immediate to the drug surface will be able to see a tightly bound layer, which is known as stern layer. Stern layer. As we move away, the diffusion of ions is seen. So this layer is known as a diffuse layer. A diffuse layer as we move away. So a diffuse layer is being created because of this movement, where the concentration of the negative ions decreases and the concentration of positive ion gradually increases. And at certain point there will be an equilibrium between the negative and the positive ions, and that region is known as electroneutral region. So now this is what's seen in a suspension having finely divided particles carrying surface charges. Now let's consider this graphically. So when we look at the same phenomena graphically, now here the particle surface having positive charge uh, absorbs negatively charged, just like here what we have seen here. Now at this point, at this surface, it is known as surface potential A. Surface potential. Surface potential is the surface charges carried by the particle, drug particle, suspended particle, and immediate to that it will absorb negative ions from the dispersion medium. See here, you'll be able to see the negative charges. So that the potential that exists between the particle and the negatively charged ion B is known as Stern potential. So as you move away from the drug particle, this negatively charged ion, it will attract positively charged ion from the dispersion medium, and because of this, all the negative, few of the negative ions will get added to the positively charged particles, and the positive particles of the dispersion medium moves away. Do always remember, here we are considering the drug particle charge, and again the particle charges that exist in the dispersion medium. Dispersion medium can have positive and negatively charged particles, negatively charged molecules, right? So whereas here the suspended particles will be carrying only one charge, whereas the dispersion medium will be having both, can carry both negative and positively charged molecules based on the ingredients which we select. It could be a suspending agents, it could be some dispersion medium. It could be viscosity enhancers. So many ingredients are present in the dispersion medium, so we'll be considering so many other like negative and the positive charges. That's how each ingredient plays a major role, and this actually decides the importance of a pharmacist, how he or she is going to select the ingredients to neutralize the potentials of both drug particles and the dispersion medium materials. So here we are able to see a surface potential and the Stern potential, tightly bound layer. Now and the next immediate layer will be able to see the zeta potential, which is really very important in deciding the stability. So now let's consider this diagram. This particle surface has positively charged and it adheres. This is the surface potential and it absorbs the negative ions. It is known as Stern layer. Now as we move away from the particle, there will be migration of ions and diffusion of ions, hence it is known as diffuse layer. It is also diffuse layer is also known as Gauss layer in few literature. So as we move away from the particle, slowly there will be diffusion of ions. So it is at this potential will be higher, see, higher, and slowly the potential will be reduced. So this is about the graphical representation of the charges. Now let's see this is known as Stern layer and this is known as diffuse layer. Diffuse layer is also known as Gauss layer in few literatures. Now there is one point where the negative ions and the positively charged ions, they exist in equilibrium, and that region is known as electroneutral region. And this kind of distribution is known as electrical double layer. So you are able to see a negatively tightly bound negatively charged layer, and again we'll be able to see a diffuse layer which include zeta potential. So this kind of existence of charges is known as electrical double layer. Double layer is seen. So actually this concept is really important to establish a stability, as we have discussed about the how these electrical charges will help in flocculation and or in few cases it might lead to deflocculation because of high potential barrier. They remain as individual entities. So the barrier should be much lesser, potential barrier should be lessened so that the particles will come closer to form floccules. It should not form tightly bound, rather it should form loosely packed. The most important concept of this is now let's discuss about the potentials that exist. Electrical double layer. In this, we have discussed about the Stern potential or the Stern layer. And then the diffuse layer. These are the two different regions seen across a suspended particles in a dispersion medium. Now let's discuss about two important more um, let's discuss about the two more important potentials that exist across the Stern layer and the diffuse layer. The first one would be the Nernst potential. Nernst potential, surface potential, is that the one that exists on the surface of the drug particle. Now let's see what is the Nernst potential. Nernst potential is the potential that actually exists as a bridge between the surface particle and the immediately absorbed negative one. So this is a Stern layer. The immediate one here is the Nernst potential. You're able to see here the Nernst potential. It is also known as electrokinetic potential. Electrodynamic. Now let's see in detail what is Nernst potential. It exists of the drug. It actually exists immediate next to the surface of the drug particle. And how far this is actually important. Nernst potential is also known as electrodynamic potential in few literatures. Why? Because as soon as the positively charged drug particle is exposed to a mixture of ions, in this immediately the negatively charged ions will form a layer, a tight layer, a dynamic layer. Electrodynamic potential is actually defined as the difference in the potential between the actual surface and the electroneutral region. The actual surface, the actual surface and the electroneutral region here, electroneutral region. So the difference between these two will be given as the Nernst potential. And the next one, the important potential, is zeta potential. It is really very important. We should always make sure that zeta potential should be much lesser. If zeta potential is higher, okay, if the zeta potential is higher, means what? The particles will remain at distant from each other. They'll not form floccules. So we should always make sure that the distance between the particles should be lessened, means the potential should be lessened. So the zeta potential should be much lesser. The potential at the surface of the solvating layer, this is called solvating layer, nothing but the diffuse layer. The potential that exists in this layer is known as zeta potential. And because of this diffusion of ions, means the movement of ions is seen. So this potential is also known as electrokinetic potential in some literature. In some literature. So electrokinetic potential is defined as the difference in the potential between the surface and the electroneutral region of the solution and the surface of the solvating layer. And So let me explain. Here we are having two different potentials called Nernst potential and zeta potential, which are really very important. Nernst potential is a potential that exists on the surface of the drug particle, and it is also known as the dynamic potential, which is given as a difference from the potential between the actual surface and the electroneutral region. Whereas zeta potential is the kinetic potential that exists at the beginning of this diffuse layer and the Stern layer exactly. So we are having a Nernst potential here and zeta potential here. We should always make sure that this potential is lessened to attract the particle. Right? Now let me explain this. Okay. Now, for example, if this is a particle and here we are having a negatively charged, right? Now immediate layer, and this is known as Stern layer, the immediate layer to next to the drug part surface is the Stern layer. So as we move away from the drug particles, we can see both positive charged and negatively charged particles, right? Now as we move away here, we'll be seeing positive and the negative, positive, negative, like this the diffusion of ions will be seen. But here a tight bound layer is seen, and the potential that exists on the surface would be surface potential, and here at the interface would be the Nernst potential. So here would be the Nernst potential. Understood? Here the between the Stern layer and the starting of the diffusion, this one is the Nernst potential. Zeta potential is exactly from the beginning of the diffusion layer throughout. This one would be zeta potential. Now we understood. Hope you all understood now. The zeta potential should be actually lessened, which indicates a lesser distance between the particles, which in turn relates to the flocculation. Flocculation means the arrangement of particles. For example, this is the arrangement, it's loosely packed, floccules together. This actually indicates a less potential barrier between the particles. So if there is higher potential barrier, the particles cannot form a network. Rather, they exist as individual entities and they get sedimented as a hard cake, and thus it is known as deflocculated suspension, which is an unstable one. This is how the Nernst potential and the zeta potential, electrical surface charges, surface free energy plays a major role in establishing the stability of a suspension. If you have any doubts regarding this lecture, you can contact me through my mail. In the next lecture, we'll be discussing about how can we apply this concept of a potential barrier in the formulation of a stable suspension. So the material for this presentation will be given along with this video. Thank you.